Hello friends, so in this video we are going to see how a race condition occur. So here is a simple definition of how a race condition occurs. So in case of a multi-threaded application, if the multiple threads write on the shared variable simultaneously, so as we know, the CPU schedules the threads on various CPU, so they may acquire or write onto the data simultaneously, or you are not aware when the data variable is been written, so that actually incorporate the condition that is called a race condition. So let's have a practical demonstration like how the race condition occurs. So I have taken I've created one thread here, right? So they have the thread ID and the thread routine incorporate here. So I am taking the maximum number of threads as 5. So let's create multiple threads here. So we'll take a loop. So for int I is equal to 0, I less than the maximum number of threads. The macro has been defined above. So then we have I plus plus, and then we take this p thread create within this loop, right? So then we need multiple thread IDs, so we need to save it here. So let's take a array of thread ID and we take it as maximum number of threads, that is 5 in this case. So then after we need to change here for I, right? And then we can pass the variable for the thread ID in here. So we'll take void star as the last parameter is void star. Then we have the address of I. So i's keep on incrementing, and we will copy this loop in case of join, because we need to join all these threads so that we get the output over to here. And here we will be taking like this, and thread ID will taking I in here. So here we are creating the 5 threads and operating on the same routine, and then we are joining our threads with their respective thread IDs. So let's change the thread routine as well. So we can say like we can print out something here like we have thread number %d. So thread 1 is begins, okay, and let's take it like this, and then we need to dereference our void argument which we have passed here, right? And now we will be taking in star here, and then we have taken argument. Let's save it. So we'll printing the thread ID alias over here, and then we can take the exit function also here, and here we can say the thread exit thing, right? And in between we will be taking a loop, right? And we'll take a variable above that. So we have unsigned. So we are taking a long variable because we are doing some operation on the data variable here, and just initialize it at 0. right? And sorry, we can take it as a counter, and then we'll say counter is equal to 0 to counter less than, let's take this counter we run for 100 loop, and then we have counter plus plus. And in this counter we will be taking a variable. So what type of variable? We'll take a unsigned global variable of the type unsigned long, and we'll take data is equal to 0, right? And next, what we want to do here, we'll take data variable and we're going to increment it by 1 each time, right? So let's save it. Now we need to print this data variable at the end of all the threads when got finished. So we'll take print f, right? And then we have the data value after execution of threads is equal to percentage long, and then we use data here, right? So what we are doing, we are creating 5 threads, we are joining these 5 threads, and depending on this routine, because every thread will process this routine and it will change the value of the data depending on the counter type. So we have taken the counter as 100 here, so each thread will run 100 times this loop and the data will be incremented by 100, right? So after the end of all the threads that execute this routine, the output should be 500, because 5 is the number of threads and 100 is a loop, so the data value will be 500. So 5 multiplied by 100, right? So let's run it once and see what's the value of gcc -o, then we have executable name, then we have thread.c, and we'll be compiling it with pthread library. Okay, it will compile. Yeah, so now just run and see what happened. So let's have thread, still getting the value of data which we have defined in here is 500, right? So let's increase this, like the counter we are going to increase by 1000, right? Now the value of data at the end of all the threads after execution is 5000. So let's save again and see whether we get that data or not. So you see here, yeah, it will get 5000. Again we try, it's 5000. So it's working fine. Let's increase this counter again by 0. Now see what happened. Let's compile again. You see here, it's not 50,000, it's 45025. So the value is being changed, right? And if you run again, the value again change. So this way it goes on changing, right? So this is called the race condition, right? So again compile, the value will be different. So how is this, this problem occurs? Because every thread that runs on the CPU will take this, will run this routine at, at any time, right? So if this 5 threads are scheduled for the 5 CPU, so that can run when that CPU become available. So it will increment the value, and that updated value will be read by the other thread, right? And vice versa. So the threads don't know when the other thread is, updating the value of data. So that is the reason, this have some ambiguous behavior. How to, rectify this problem is to use the locks here. So we need to kept this data within the locks. So these locks are called mutexes, and we have to lock and unlock for each thread. So when one thread comes here, it will, increment the data. When that thread got finished, then only the other thread will increment this data. So this is, the way how we can rectify this problem. So in order to rectify it, let's take a mutex. So we are taking pthread underscore mutex underscore t, and we take a mutex here and just initialize it as pthread mutex initializer. So this is a shortcut for initializing the mutex. And in this section, we will be in the lock section, we will be taking pthread mutex lock, and we'll be taking the address of the mutex here. And in the unlock section, we need to take pthread mutex underscore unlock. Okay, and we'll be taking it as address of the same mutex, and let's save it, right? So once we compile it again, you will get 50,000 here, right? So again and again you will get the same value. So if you see here, the thread IDs are not in sequence, so you are getting 1 and all 5 shares. This is due to the printf. So it's not a very good process like to use printf in the thread function. So in order to rectify this for a while, so we can use the fflush for the std out stream after each printf. So once we do that, fflush, and then we have std out here, and let's save it, and again we run it. And once we do it, so after using this fflush function, we have 5 thread with begin and 5 thread with exit, but it depends on which thread will take which core and the availability of the core at that time. So these prints are not in sequence, so that is a noun behavior, but the output, if you see, it's same for each of us. So thanks for watching this video.